Okay, another molecular scene problem. So using molecular scenes to find quantities at various times. So again, this picture shows us that we have a substance, green, decomposing to two other substances, B, blue, and C, yellow. I'm actually going to call these G, B, and Y rather than A, B, and C, just as it's going to be easier to make sure we keep our colors straight. They tell us that it's a first order gaseous reaction, and the molecular scenes show a portion of the reaction mixture at two different times. So t equals 0 seconds is the start of the reaction, and t equals 30 seconds is sometime in. So the first problem here asks us to draw a similar molecular scene of the reaction mixture at 60 seconds. So first let's kind of look and see if we can figure out what's happened kind of going from 0 seconds to 30 seconds. So if we kind of look at what's happened here, we can see well, we had 8 green spheres, so 8 gas particles that were green, and they decomposed so that at our 30-second time point, we had 4 of these green particles, 4 of the blue particles, and 4 of the yellow particles. So the important part of kind of looking at what's happening here is that we can realize that the reactant is half gone. And that's important because that tells us that this time frame, 0 seconds to 30 seconds, is 1 half-life because we went from 8 greens to 4 greens, so half as much. So that's an important part to this problem because that tells us we've gone through 1 half-life. So if we want to go to 60 seconds, we've gone through a second half-life. So again, this is 1 half-life. So again, t equals 30 seconds passed. For time equals 60 seconds passed, we're going to go through a second half-life. And if we kind of, think about this equation, and what this really means, it means 4 greens broke down into 4 blues and 4 yellows. So that really the equation is 1 green breaking down into 1 blue plus 1 yellow. That's the net of what's happening in this chemical equation. So again, if we think about what happens at time equals 60 seconds, a second half-life, we're going to have half of our reactant break down again. So we're going to be left with only 2 greens. And 2 greens, again, means we're going to make 2 greens is going to break down to 2 blues and 2 yellows. So we need to add that to here. So then we're going to get 6 blues and 6 yellows. Okay, so this problem asked us to draw a molecular scene at time equals 60 seconds. So again, time equals 60 seconds. Okay, now we're only going to have 2 greens. So I've got my green here. So we've only got 2 greens that are left. We're going to have 6 yellows. 1, 2, 3, 4, 5, 6. And 6 blues. 1, 2, 3, 4, 5, 6. Okay, so that's our molecular scene for the reaction at 60 seconds. Part B asks us to find the rate constant of the reaction. Now, what's important to this is the fact that they tell us that it's a first order process. For a first order process, we can use the equation that the half-life is directly proportional to the rate constant with this equation. So again, we want to find the rate constant, which means we're going to use the other version of this. And so we can take 0.693 over what we know the half-life to be. We know that the half-life is going to be 30 seconds. And so the rate constant is 2.31 times 10 to the minus second per second. Okay, so that's part B. Part C says, if the total pressure of the mixture is 5 atmospheres at 90 seconds, what is the partial pressure of the substance B? Okay, and again, that's going to be our blue spheres. Well, let's go back to our top equation here and say, well, what happens at then time equals 90 seconds? Again, one more half-life. We're going to have half of our substance, our reactant, disappear. Now that's only 1 green, so we're going to be down to 1 green, and the 1 green that reacted will make 1 more blue and 1 more yellow. So this is the mixture that we'll have at time equals 90 seconds. So one of the things that we have to remember back from our gas chapter is when we're talking about total pressure is really the sum of the partial pressures of all the individual gases that are there. So in our case, we're going to have a partial pressure that's contributed by green, plus a partial pressure that's contributed by blue, plus a partial pressure that's contributed by the yellow. And partial pressures here, so the partial pressure of green is going to be equal to the mole fraction that we have of green times the total pressure. And we can do that for the rest of these. And again, we'd like to know the partial pressure of substance B. So that's going to be the partial pressure of B is going to be equal to the mole fraction of B times the total pressure. So you might want to figure out, well, how can I figure out mole fraction? There's nothing in this problem that indicates anything about mole fraction. But remember, when you have molecular scenes and they tell us that it's a gas reaction, we can count particles and use that to figure out partial pressures. So at time equals 90 seconds, we have 15 gas particles. Okay, we have 15 gas particles, 1 of them green, 7 of them blue, and 7 of them yellow. So if we want to find the mole fraction, that's blue, this is the total number of blue gas particles over the total number of gas particles, which in this case is 7 over 15, or 0.467. So remember, mole fraction for gases is really kind of the percent of the mixture that's taken up by these gases. Gases are so far separated that we really can count individual particles and we really can have a percent of this. So 46.7% of our gas mixture here at 90 seconds is taken up by the blue particles. So we just said here that the partial pressure of gas B is going to be equal to the mole fraction, which we just figured out, times the total pressure, which they told us is 5 atmospheres. So again, the partial pressure of gas B is going to be equal to the mole fraction, which is 0.467, times the total pressure, which is 5.0 atmospheres. So the partial pressure of gas B is going to be 2.33 atmospheres.